What's up guys, it's me Sir Ernest, and today we're going to talk about potential energy. So let's recall that if a particle moves from one point to another under an influence of a force, the work done on the particle by the force is equal to the line integral of the force function f, so function of r, along dr from point 1 to point 2. Now, in many physical systems, the force F has a property that the work needed to move a particle from position 1 to position 2 without any change in kinetic energy depends only on the initial and final positions and not the path taken by the particle. So either the particle moved in this path, along this path, or along this path, the work done on the particle by this kind of force would still be the same. Now say, for instance, a ball, which we're going to consider to be a particle, is raised from the floor to the top of a table. Okay, and let's say that table has height h. So here we're going to consider the floor to be our reference position. Now from here we can analyze the situation by considering first that the mass of the ball is m, so that at any point within this path there's always a force acting on it, that is downward. That force is your gravitational force. Now, under the influence of this constant gravitational field or force, the amount of work has to be done on the particle given by mgh, so that it can be raised to this height h. Now, since the gravitational force exerted on the particle will do the same amount of work on the ball, so this capacity to do work is what we call the potential energy of the particle. And this is always associated with the force like your gravitational force. So in one dimension, for example in this case, the work done is actually equal to the applied force or work done by the force F from your initial position to your final position to be F x dx from x naught to x, and is defined as the change in potential energy x naught minus u x naught. Okay, so let's say for example we're looking at the work done exerted by gravity as this object, as this, let's say, ball falls down on the ground. Okay, so in this case the force would be equal to mg, and then the direction, let's say, is downward, so that's negative, and the force is negative. So the product between the force, gravity, and dx would be positive. So that means the work done would be the integral of mg, so it should be mg dy from h to 0. So when you integrate this, this becomes mgy integrated from h to 0. again, our reference point here is the floor. So this becomes mg negative mgh. Sorry, mgh. So this is now the work done with the force, which is equal to the potential energy of the particle at y equals h. Now, as you can recall, okay, here we take note that the speeds of the particle at initial position and your final position are 0, because again, remember, from the beginning until the end, from here to here, the ball are at rest. That means there's no net change in kinetic energy. Now, from here, you can actually define that this is now equal to negative initial potential, final potential energy minus initial potential energy. So this is negative delta E. So if this happens after small amounts of x, we can now define a certain force associated to this potential energy to be equal to negative derivative of u, which is a function of x with respect to x. Okay, so this is now the relationship between your force and your potential energy, and we call these forces a conservative force, and we're going to talk about this in the next video. So if you have a conservative force, there is always an associated potential energy with it. Okay, so that's it. That's your conservative force and the relationship between the conservative force and your potential energy. Okay, so that's all for now. Thank you guys for watching, and I'll see you guys in the next video. Bye-bye.